what we've discussed so far is really how a neuron fires and how a neuron makes predictions. And we said that it does so essentially with our linear function. And what our linear function does is we take in different features of an observation, like here, cell area and cell concavities, how many bumps there are in a potentially cancerous cell. We multiply each of those features by a corresponding weight, right? So the first feature we multiply by W1, the second feature multiply by W2, and then we add this counterbalance, which is our bias term. And this is our linear function. And if our linear function returns a value greater than 0, then we say that our neuron fires. And if our linear function returns a value less than 0, then we say it does not fire, right? So if it's greater than 0, we return a 1, less than 0, we return a 0. So this is just me showing this, W1x1, W2x2 plus b. And we said we could kind of rewrite this using the dot product. And just to expand this is our weight vector, this is our feature vector, plus the bias. So this is showing it's exactly the same thing as above. And just an example, right? Let's say, our weights are 2 and 1, and our features are, cell area is 3, and the number of bumps is 4, and we have this counterbalance our bias as -5. And then again, we just pair up the terms, multiply them, add the products, and then finally add our bias term. Okay. One thing we've been, we've been a little fast and loose about is that we've always just said, oh, well, this z is going to output a number, positive or negative. Here it outputs a 5, and because it's a 5, that somehow translates to like a 1, right? Because it's a positive number, that means that neuron fires. And if it's a negative number, then it means the neuron does not fire. But that logic should really be represented in code. So let's do that. After all, we did represent our linear function in code by doing w.x plus b. So now what we should do is also represent our activation function in code. So that's this logic of firing or not firing. So this is what happens, right? We have a linear function. We pass in our feature vector x to our linear function. This is going to output a number. Here's our positive number. Now we want to take that let's assign this to z. So now we want to take this positive value and pass it through our activation function. And if you think about the logic, well, we said that if this value is greater than 0, then we return a 1. And otherwise, we return a 0. That's it. Okay, so now putting this together, we can see, okay, well, here's our linear function. Let's actually print. I like sometimes printing out the output. And then here's our activation function. Okay. So and here, well, might as well get that feature vector too. All right. So we take the features, pass it through a linear function, get some sort of output, either a positive or negative number, and then turn that positive, negative, or negative number into a 1 or a 0, meaning our neuron's firing or not. That's what you can see, is that our linear function gives us the number 6, greater than 0, turn it to a 1, meaning here our neuron fires. Now, one thing that we should point out, so I define the activation function, that it directly determines the output of our neuron. Here it's directly, this is what our neuron really is sending to other neurons. It's the number 1, right? So the activation function directly determines the output of our neuron. Now there's of course always an issue, and here the issue is that we don't really want to return an all or nothing response, right? We either have two options right now. Either the neuron fires or does not fire. But if you think about our example of, we're trying to predict whether or not a cell is cancerous, lots of times the doctor does not come back and say, yeah, 100% cancerous. Lots of times he wants to know, a likelihood of it being cancerous. So what I like to think about is essentially that we're going previously we returned a 1 or 0. Essentially, our neuron, if our neuron's lighting up, it either is basically an on-off switch. Either it lights up or it doesn't. But what we want to go to is a dimmer, where we can kind of say, yeah, like we're this bright because we are that confident that this cell is cancerous, or we're quite dark, but maybe not exactly off, because we are quite confident that the cell is not cancerous. So that's our goal. And just to kind of break this down mathematically, previously with our activation function, as you can see, right, this is returning a 1 or a 0. But what we want to do really is go to, it doesn't matter how small it is, always returning a 0. But what we want to do is we want to go to have this activation function return a range between 1 or 0, where like a value of 0.1 or 0.01 means we're quite confident that not cancerous, or that basically we're just quite confident in the negative direction. And here we're quite confident that cancerous, right? And then here we are basically shrugging our shoulders. We are unsure. So if we're really confident that that this cell, that this observation is cancerous, the best we can do is return a number close to the value 1. And if we're really confident that it's not cancerous, the best we can do is return a value close to 0. And to express that we are unsure one way or the other, what we do is we return a value that's close to 0.5. So that's, what does something like that is not this, we still have this linear function. That actually is in pretty good shape, because I can, start with this vector x, pass this through my linear function, get an output, okay, like 2, and then take that output, and that so far is good. What's bad is really this activation function, because this activation function is now going to take that 2 and give us that all or nothing response again, okay? So that's what we want to change. So currently if it's greater than 0, return a 1, otherwise return a 0. And what we can instead replace this with is something called the sigmoid function, okay? And in the reading I go into more detail about what this sigmoid function is, how it works under the hood, so you can take a look at that. For now, let's just explore it and see if it kind of has this desired effect of returning numbers close to 0 or close to 1 based on how confident we are. So now, here we're returning the value 2. Let's try this again. We'll copy this down below. And this time, if we pass through this value, we're going to get a 2, and that 2 is going to translate into 0.88. You see that? So value close to 1, which makes sense. We're returning this linear function is outputting a number, higher than 0. If the linear function outputs, let's just pass through, let's say we make this smaller. Okay, so now let's see what this outputs. Oh, look at that. Outputted exactly 0, right? So it's 0 on the dot, neither positive nor negative. Then our prediction is actually 0.5. That was a nice example, right? We are expressing uncertainty. And now if we go even smaller, well, now the linear function is outputting a negative 3. And our activation function is taking that negative 3, passing it through this sigmoid function, and returning a number close to 0, right? 0.04 is pretty close to 0. So this is basically saying, 4% chance of cancer, meaning we're pretty sure there is not cancer here. Okay, so that's really achieving the output that we want. And this is the hypothesis function of a neuron that we will be using. We'll be taking in features from an observation, passing those features into the linear function, where the linear function is really just employing the dot product, right? And then we are going to pass the output of that into the sigmoid function. So this is going to be, let's just call this z, and then you pass that output from our linear function into the sigmoid function. One thing I want to kind of express is that the linear function can really output any number from negative infinity to positive infinity. But then the sigmoid function is going to compress, these values down to a range between 0 and 1. So it has this squishing effect, which you could see, right? Here we had this -3, and we kind of squished this down to a value close to 0. Previously, we outputted that number 2, and we squished it down to a number like 0.9 something, all right? So that's it. That's really what's the hypothesis function of our neuron. If you wanted to, right, we could write this as the hypothesis function of our neuron passed through x, and then here's our z, and then we just return the activation function, and it has the same output. Okay? So that's really how you can think of a neuron's hypothesis function, is that it consists of two components, or two layers. The first layer is the linear function, and the output from that linear function is passed to an activation function. And that's it. That is are the components of a neuron's hypothesis function. And as I said, if you want to learn more about this sigmoid function, maybe just briefly, we should just say the sigmoid function is represented oftentimes by the Greek letter sigma. And here it's just taking an input, I call it x, but in our example, this is, z, right, the output from our linear function. So what that means is you can express the entire function as, the entire hypothesis function as this, w dot x plus b, and then pass this output into the sigma function. And as you'll see in the reading, the sigma function is really this guy right here. So I'll stop myself from going deeper into this, but good work. This is the hypothesis function of a neuron, and what's next for us, we go to jigsawlabs.io and click on free curriculum and scroll down, is building our first neural network. So that's going to be pretty fun. All right, I'll see you guys in that lesson.